Good morning, students. We have looked at the formulas for solving problems on heat engine and also for solving problems on refrigerator. In this video, we are going to look at a problem where you have a system which is a combination of heat engine and refrigerator. You all know that a heat engine is a device that is used to convert the heat energy into useful work. And the refrigerator is a device which transfers heat from a low temperature body to high temperature body with a work input. So here what happens in the combined system, the output of the heat engine, let me say W1, the useful work output of the heat engine, right, is given as input to the refrigerator. So this work input is required for the refrigerator to transfer the heat from the low temperature body or cold reservoir to high temperature body or hot reservoir. So let us look at the problem, what is given in the problem and what we need to find out. Now let us look at the problem number 6 and try to understand the data given in the problem. A reversible heat engine operates between two reservoirs at 827 degrees Celsius and 27 degrees Celsius. First, the heat engine and the corresponding reservoir temperatures are given, right? So we all know that theoretically we assume the heat engine to work between two reservoirs, two thermal energy reservoirs. One is called as source and the other one is called as sink. So the temperatures of source and sink, the two reservoirs, are given here. Next sentence, engine drives a Carnot refrigerator maintaining minus 13 degree and rejecting heat to a reservoir at 27 degrees Celsius. In the second sentence, a refrigerator is given, right? Details regarding the refrigerator is given, right? Similar to a heat engine, refrigerator is also a cyclic device which operates between two reservoirs, right? Usually we call the reservoirs as low temperature body and high temperature body. But in this problem, I have named them as cold reservoir and hot reservoir, right? Okay. What is the contrast between heat engine and reservoir? You all know well. Heat engine receives heat from hot reservoir, converts the heat received into partly into useful work and rejects some amount of waste heat to the cold reservoir. Refrigerator transfers heat from a cold reservoir to hot reservoir. For transferring this heat, a work input is required for the refrigerator. So this is the contrast between a heat engine and a refrigerator. Coming to the second sentence of this problem, it is given that a refrigerator is maintaining minus 13 degree. This minus 13 degree is the temperature of the cold reservoir. The cold reservoir we always understand as the refrigerated space inside the refrigerator. So this minus 13 degree is the temperature of cold reservoir, which is understood as the refrigerated space inside the refrigerator, and rejecting heat to reservoir at 27 degrees Celsius. The refrigerator absorbs some amount of heat from cold reservoir and it rejects to the hot reservoir, right? So here two temperatures are given. minus 13. We have seen this temperature minus 13 is the temperature of cold reservoir. Therefore, 27 degree should be the temperature of hot reservoir. In the third sentence, heat input to the heat engine is given as 2000 kilojoule, right? And the net work available is 300 kilojoule, right? So here I have drawn a heat engine block diagram and refrigerator block diagram. The work output of the heat engine is connected to the refrigerator as the work input for the refrigerator. Okay, right. In the third sentence, the heat input to the heat engine is given as 2000 kilojoule. So I can take this 2000 kilojoule as Q1. Net work available is 300 kilojoule, right? So whenever the term net work available is given in a combined refrigerator heat engine system, the net work indicates the work subtracted between W1 and W2. Okay, we know that the W1 is the useful work output from the heat engine. W2 is the work input required for the refrigerator, right? If you subtract W2 from W1, what is the work remaining? That is called as the net work available. So whenever the term net work available is given in combined heat engine refrigerator system, so it can be taken as the difference between work output of the heat engine and the work input to the refrigerator. Going to the fourth sentence, how much heat is transferred to the refrigerant and the total heat rejected to reservoir at 27 degrees Celsius. Okay, the first question is heat transferred to the refrigerant. What is refrigerant? First of all, refrigerant is a working substance used in a refrigerator, right? So it the refrigerant circulates through all the devices that are present in a refrigerator. So assume that the refrigerant is present inside the refrigerator. Heat transferred to the refrigerant means the heat added, right? To the refrigerant means heat added to the refrigerant. So therefore, I need to find out Q4. Then the second question, total heat rejected to reservoir at 27 degrees Celsius, right? So how much heat is rejected or added to the reservoir at 27 degrees Celsius? So you have to look at which reservoir is at a temperature of 27 degree and what is the heat rejected to that reservoir. That one we have to find out. Okay. So what we have to do, we have to draw a block diagram in this way. Okay, and you should be very careful with this term net work available. If the term net work available is given, as I already told, it should be taken as W1 minus W2. In some similar problems, combined heat engine refrigerator problems, what they will give is they will give like this: the work output of the heat engine is given as the work input to the refrigerator, or they will give like this: heat engine drives the refrigerator. So both these sentences or statements mean the total work output of heat engine is going completely as input to the refrigerator. Okay, So there is no remaining work. After supplying some work to the refrigerator, there is no remaining work. So that is another way of giving the data. So when net work is given, it means that after supplying some work to the refrigerator, some more work is remaining. So that work is taken as W net, which can be written as W1 minus W2. So this is how we have to draw the block diagram for a combined heat engine refrigerator problem. Okay. For heat engine, we have two reservoirs, hot reservoir and cold reservoir. Similarly, for refrigerator, we have two reservoirs, cold reservoir and hot reservoir. Right? We can give the notations as shown in this figure. For heat engine, the hot reservoir temperature can be taken as T1, cold reservoir temperature can be taken as T2. Heat received from hot reservoir can be taken as Q1 and heat rejected to the cold reservoir can be taken as Q2. And W1 can be taken as the useful work output from the heat engine. As far as the refrigerator is concerned, T3 can be taken as the temperature of hot reservoir and T4 can be taken as the temperature of cold reservoir. And then regarding the heat transfer terms, Q4 can be taken as the heat absorbed from the refrigerated space or cold reservoir. Q3 can be taken as the heat rejected to the hot reservoir. Okay, and here T1, T2, T3, T4, the temperatures of all reservoirs are absolute temperatures. That means it should be in Kelvin. Even though the temperatures are given in Celsius, we need to convert to Kelvin. In this problem, we need to find out first the heat transfer to the refrigerant, that is Q4, heat transfer to the refrigerant Q4. Then secondly, we have to find out the total heat rejected to the reservoir at 27 degrees Celsius. Here, two reservoirs are at 27 degrees Celsius. One is the cold reservoir of heat engine and the other 27 degrees hot reservoir of refrigerator. So these two reservoirs are at 27 degrees Celsius. So total heat rejected to reservoir at 27 degrees Celsius means I need to find out Q2, Q3 and add those two. So total heat rejected to reservoir at 27 degrees Celsius is equal to Q2 plus Q3. First, let us write down the data given in the problem. First, let us write down the reservoir temperatures, right? For heat engine, the reservoir temperatures are given as T1, the hot reservoir temperature is given as 827. Okay, I have to add 273 for converting to Kelvin, so which is equal to 1100 Kelvin. Then the cold reservoir temperature is given as 27 degrees Celsius. Again, I have to convert to Kelvin, equal to 300 Kelvin. Okay, then the heat input to the heat engine is given, which is taken as Q1. This is equal to 2000 kilojoule. Okay, then for a refrigerator, the reservoir temperatures are given. So we have taken T3 as the hot reservoir for refrigerator. The temperature of hot reservoir for refrigerator is 27 degree, adding to 73, so I get 300 Kelvin. Cold reservoir temperature is taken as T4 minus 13 degree plus 273 equal to 2 260 Kelvin. Then in addition to these data, they are given the net work available, which we have taken as W1 minus W2, that is given as 300 kilojoule. So we have written all the data given in this problem. So now we are going to calculate the efficiency of heat engine. So let me start step 1. In step 1 I am going to find out the efficiency of heat engine. Right? I know the reservoir temperatures, so I can use this formula 1 minus T2 by T1. Right? So substituting the values, 1 minus 300 by 1100, I'll get 0.727, or by multiplying 100 I can convert this to percentage. In step 2 I am going to find out the heat rejected by the heat engine to the cold reservoir. Okay, so that is going to be my step 2. So always keep it in mind the parameters we need to determine: Q2, Q3, Q4. These are the three parameters we need. So what I do, I am going to use the other formula to find out the heat engine, which is in terms of Q1 and Q2. So I write eta He equal to 1 minus Q2 by Q1. Right, so from this I am going to find out Q2. Right, so let me substitute the values. 0.727 is equal to 1 minus Q2 by Q1 is 2000. Right, so I can simplify to get the value of Q2. Q2 is equal to 546 kilojoule. Right. In the next step, I am going to find out the work output of the heat engine. Right. So that is W1. Right. So for a heat engine, the work output is equal to the net heat transfer. So I can write the net heat transfer as Q1 minus Q2. Right. So Q1 is 2000, Q2 is 546. Therefore, the work output of the heat engine W1 is equal to 1454 kilojoule. So far, we have calculated three parameters associated with the heat engine. In the first step, we calculated the efficiency of heat engine. In the second step, we calculated the heat transfer Q2, and in the third step, we calculated W1. Two more parameters we need to find are Q3 and Q4. Q3 and Q4 are associated with the refrigerator. So what we can do to find out Q3 and Q4? Right. So here I can find out COP using the hot reservoir and cold reservoir temperatures, COP of refrigerator, right? And then if I know the value of W2, I can find out Q4, and then I can find out Q3. So in the next step, I am going to find out the COP of refrigerator. So let us write the formula. Step number 4, I am going to write the formula for COP of refrigerator, right? Yeah, just to have a better understanding, let me write from this point. COP of refrigerator is equal to the desired effect, that is the heat absorbed by the refrigerator, here it is Q4, divided by work input, here it is W2. Okay, and this W2 can be written as the difference between the heat rejected and heat absorbed. Okay, heat rejected by the refrigerator is Q3, heat absorbed by the refrigerator is Q4, right? So COP of refrigerator can also be written as Q4 divided by Q3 minus Q4, or otherwise I can write in terms of absolute temperature, just replacing the heat transfer terms Q3 Q4 by T3 T4. So I can write like this: T4 divided by T3 minus T4. So now I am going to use this formula because I know the cold and hot reservoir temperatures of refrigerator. Okay, so what is the value of T4? It is 260. T3 is 300. Upon simplification, I'll get the value of COP of refrigerator as 6.5. Okay, so this is we do in step number 4, and in step number 5 we are going to find out Q4, right? So let me write step number 5. In step number 5 I am going to find Q4. How I am going to find Q4? So let me use the first formula which I have written here. COPR is equal to Q4 divided by the work input W2. Here in this formula, the value of W2 is not known. So first let us find out W2, right? So we know that W1 minus W2 is equal to 300 kilojoule, and we have already determined the value of W1, that is the work output of the heat engine, right? So we determine the W1 as 1454 kilojoule. So now what I can do, I can find the value of W2 from the above two values, right? So I get W2 is equal to 1454 minus 300, which will be equal to 1154 kilojoule. Now I know the value of W2 and the COP of refrigerator. So knowing these two values, I can find out the value of Q4. So therefore Q4 is equal to COP of refrigerator multiplied by W2. COP is 6.5 multiplied by 1154, right? The value of Q4 is equal to 7501 kilojoule. Next, we are going to find out Q3. So that is going to be the step number 6. So step number 6, I am going to find out W2. I hope you remember we have written the work input of the refrigerator as Q3 minus Q4. Heat rejected by the refrigerator minus heat absorbed by the refrigerator. Okay, right. So what we are going to do now is to find Q3. So therefore I write Q3 is equal to W2 plus Q4. Value of W2 is 1154 kilojoule and Q4 is 7501, and therefore Q3 is equal to 8655 kilojoule. Yeah, and now we got the three required parameters Q2, Q3, Q4. So now let us write down the answer for this question. The answer for the first question, right? Heat transfer to the refrigerant. Heat transfer to the refrigerant. This is equal to Q4. The value of Q4 is 7501 kilojoule. Then the second question is total heat rejected to the reservoir. Total heat rejected to the reservoir at 27 degrees Celsius. So this is equal to the sum of Q2 and Q3, which is equal to 546 plus 8655, which is equal to 9201 kilojoule.